All right, so our horizontal asymptotes. So we previously saw that as x approaches negative infinity, denoted as x arrow plus or minus infinity, a polynomial will begin to act like its leading term. So we can extend this further and say that given a polynomial function, so looking like this, what will happen is that as x goes to positive or negative infinity, so it just keeps on growing, what should happen is that this function really should start acting like its leading term. So we're going to use this to help us figure out where horizontal asymptotes would exist. So horizontal asymptotes are kind of like vertical asymptotes. They're lines that you approach. You can cross them in the case of horizontal, but eventually they're a point that you I can't cross any longer. The line y equals b is a horizontal asymptote for the graph of f if either or both of the following are true. Fx approaches b as x goes to infinity, or it approaches b as x goes to negative infinity. So sometimes horizontal asymptotes are only one-sided. If the numerator and the denominator of the rational function have the same degree, the line y equals a over b is a horizontal asymptote where a and b are the leading coefficients of the numerator and the denominator, respectively. So we're going to demonstrate what that means. So, like I said, as we go to infinity, we should behave a polynomial like its leading term. So if I gave you this rational function, remember the top and the bottom are both polynomials, and I said x is heading towards negative infinity, what we should see is that this term on the top takes over and this term on the bottom takes over because they are the leading terms of those polynomials. So as x does approach positive or negative infinity, it kind of varies. What we should be seeing is that this whole function starts approaching a function that looks like this. It starts approaching, well, x over x cubed over 2 over x cubed. Once again, because it's looking like this, well, those will cancel themselves out, and what we're really left with is this polynomial is going to approach 3 over 2, which means that we are going to have what we call a horizontal asymptote at 3 over 2. So I have it graphed here for you. So what we see, it's hard to tell, but that's 5. So this is 1, this is 2. So this is roughly 3 over 2 or 1.5. So what we see is the blue line is representing my asymptote. What the graph does, like I said, it can cross here, but overall what we're seeing is that as we're moving out towards infinity, it's just moving steadily closer to that asymptote, but it doesn't cross it. So that's how a horizontal asymptote behaves. As I said, you can cross it on a small scale initially, but once you start heading out toward infinity, you don't cross it again. You just get infinitely closer to it. But your horizontal asymptotes are always going to be y equals because they're always going to be these horizontal lines. So let's do this again, but now we have a case. So the first one we were looking at is that the top and the bottom have the same degree. Now what we have is that the top has a smaller degree than the bottom. So what happens in this case as x goes toward infinity is that the top will start behaving like 6x squared, the bottom start behaving like 7x cubed. So overall, it's behaving like these two functions. We have a quotient of these two. Well, if we simplify this, get rid of some of my x's, I'm just left with 6 on top and 7x on the bottom. So that means as x gets larger, so if x is 1, then we'd have 6 over 7. If no, it's not quite it, but like I said, if x is 1, then you'd be looking at this as being 6 over 7. If x was 2, then we would have 6 over 14. If x was 3, then we would have 6 over 21. What we see is the bottom keeps growing and growing and growing. And this fraction keeps getting smaller and smaller and smaller. Oops, just a second. There we go. So this is roughly about approximately 0. We'll say 86. This is approximately 0.43. This is approximately 0.29, but as you see, that fraction just keeps getting smaller and smaller and smaller. So what we have here is that as x increases, 6 over 7x becomes smaller and smaller, and it's approaching 0. So instead of saying equals 0, that really should have been approaches 0. This means that there is a horizontal asymptote at x equals 0. Or sorry, y equals 0. I said the okay. So y equals 0 is graphed in the blue. It's a little hard to see there because it's sitting right on the x-axis. Here, let me do that again in blue so we can see that a little better. But what you see here is what's my function is doing once again is it may have crossed initially, but it comes down, but it steadily gets closer and closer and closer and closer to that x-axis, or y equals 0. Same thing over here. It comes up, but then it comes down and it gets infinitely closer and closer and closer. So we do have a horizontal asymptote at y equals 0. And so for our last one, we have a higher degree on top than on bottom. So once again, if I'm heading towards infinity, these two terms are taking over on the top and bottom. So as I head towards infinity, I end up with x cubed over 3x squared is what I'm approaching. If I simplify that, I'm left with an x on top and a 3 on bottom. So what this case you see is that as x is getting larger, my fractions are also getting larger here. So like I said, it's just getting bigger and bigger and bigger. Oops, so there was a weird typo over here. I'm not sure what I was doing. So like I was saying, it's just getting larger and larger and larger as x's get larger. So as x increases, x over 3 becomes larger and larger, and eventually it starts approaching infinity. This means that I have no horizontal asymptote in this case. Because to have an asymptote means I have to have a point that I slowly approaching for infinity, and I'm not slowly approaching anything. I'm just shooting off towards infinity. So this is the graph of this one. Like I said, there really isn't a horizontal line that we're approaching. We're just shooting off to infinity here and here, and here and here. So we got some vertical asymptotes, but we don't have any horizontal asymptotes. I do not have a horizontal line that we approach. So like I said, that's kind of the explanation for this here. So when the numerator and the denominator of a rational function have the same degree, the line y equals AB is the horizontal asymptote, where A and B are the leading coefficients of the numerator and the denominator, respectively. So that's what happened. The first ones, both of them were degree 3. The leading term took over, so it was just a quotient of the leading coefficients. When the degree of the numerator of a rational function is less than the degree of the denominator, then what happens is that the x-axis, or y equals 0, becomes my horizontal asymptote. So like I said, in that case, what happens is the bottom grows faster than the top. So it forces the whole rational function to get smaller and smaller and smaller, and it gets closer to 0. When the degree of the numerator of a rational function is greater than the degree of the denominator, there is no horizontal asymptote. So in that case, what we saw was that as x's got larger, the the ratio that we had made started getting larger and larger and larger as well. So it wasn't approaching any value, it's just shooting off to infinity. So for an example, we want to see if we can find the horizontal asymptote of this function. So like I said, what you could really kind of do is just take your leading terms. So as x goes towards infinity, my leading terms take over. If I simplify my leading terms, I'm just going to end up with 2 over 3. So my horizontal asymptote is y equals 2 over 3. So take a minute, and you have 3 different functions here. This one actually should have been an h, so there are definitely 3 different function names. So that was a little bit of a typo. That's like it's saying, do each one of them and try to assess what your horizontal asymptote is, if in fact it exists. All right. So for the first one, like I said, we see that the degree on top is bigger than the bottom. So if we're looking at x going towards infinity, this starts behaving like x to the 4th over 3x squared, which is the same as x over 3. Which means that as x is getting bigger, this is getting bigger too. We have no horizontal asymptote. For B, the degree on the top is smaller than the bottom. So let's say x is going towards infinity. This should start acting like 7x to the 4th over 3x to the 5th, which then we simplified would be 7 over 3x. So that means as my x's are getting larger, the bottom's getting larger, but the overall fraction's getting smaller. That one should be heading towards 0. So my asymptote, horizontal asymptote, should be y equals 0. And then for the very last one here, as x heads towards infinity, this should start acting like these leading terms. We've had 12x to the 5th over 4x to the 5th. If we had simplified this, and notice that they have the same degree, if we simplified, we'd be left with, these would cancel out. I have 12 over 4, so I would just have 3. So this means my horizontal asymptote is y equals 3.